Hello class, this is Mr. Hunter and this is your Electrodynamics notes part 4 and will be the last part of electricity. Just very briefly, because I wasn't able to get this into your last video, I wanted to give you kind of like a general hint that can help you figure stuff out. So in a parallel circuit, the total resistance will always be smaller than the smallest resistance. So right here, please make sure you copy this notes as well as the math into your notes so that you can use it for studying in the future when you forget this stuff, because you inevitably will. Some of you will remember because you're good students. In a parallel circuit, remember, electrons can take multiple paths. I have a 2 ohm resistor, a 3 ohm resistor, and a 4 ohm resistor. So when I use the equation for a parallel circuit, it's 1 over total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. And so when I plug that in, I get 1 over total resistance equals a half plus 0.33 plus 0.25, and I get total resistance equal to 1.08 ohms, or 1 over the total resistance. Now that I have to take the reciprocal of that, it really turns into total resistance is 1 over 1.08. And so the total resistance is 0.93 ohms. And as I stated, the total resistance is smaller than the smallest resistance for parallel circuits because that's how the math works out. So if you ever get a resistance that's higher than one of your resistance for a parallel, you know you did something wrong. In the same way, series circuit is the total resistance is always greater than the greatest resistance. Why? Because you're adding up the total resistances. So the total equals R1 plus R2 plus R3. Now remember, like, everything has resistance. So like if you have a lamp, it actually has a resistance. We can consider a resistor or just the resistor itself. So the last part of what I wanted to show you or need to show you is about magnetism, because technically this unit is electricity and magnetism because they're related. They're related in first that a magnet creates a magnetic field around it, and the magnetic field lines come out of north and into south. So the way to equate it is like, hey, you know positive and you know negatives. You can almost equate it the same way here. So magnetic field lines always go out of north, and they go always point towards south. So this would be like positive and negative, right? But it's magnetic, not electric boogie woogie. So they go out of the north and into the south. Now, here's what's really cool about a magnet. When you break a magnet, and if you've ever played with a magnet, when you break it, one side doesn't become like non-magnetic. If you actually break a magnet, what ends up happening is it becomes north and south again. So if I were to break this magnet down the middle, the north side would stay north, but the opposite end of the magnet would now become south. And same thing with the other part of the magnet. The broken part would become north and the other side would become south. And so this is called a magnetic dipole. Theoretically, a magnetic monopole should exist, but we have not been able to break down a magnet such that we can only get a north or only get a south. We always get the north and the south when we break down a magnet. So here's the really, really cool thing, an application to real life stuff that how we actually make electricity. A moving magnetic field causes charges to flow, aka a magnetic field pushes electrons through a wire, causing a current. So when we see this in Friday in class, or whenever we are going over this homework in class, what you're going to see is I'm going to break out this little device I made where I took a film canister, I put some magnets inside, and then I wrapped a bunch of copper wire around the outside and then attached it to a small LED. And what you'll see is the LED lights. You've seen the same thing where you have like crank flashlights, because what's really happening is there's a magnet inside that's connected or inside a bunch of wire, and the wire is connected to the light bulb so that when you crank it, the magnetic field or the changing magnetic field pushes the electrons through the wire, causing a current, making electricity, which goes into something that we haven't really done in a while in physics because they kind of took it out the standards, but I'm going to teach it to you anyways. And the rule is called a right-hand rule, because in the right-hand rule, you point your thumb in the direction of the current, and you, using your right hand, your thumb gets pointed in the direction of the current, and your fingers wrap around the direction of the electric field. So if the current's going up through this wire, then the electric field would actually be going, let's see, it would be going counterclockwise around the coil. So remember, we have an electric field, so we have an E field that we've talked about before. And now, since we have magnets, wow, I can spell, I swear. And now that we have magnets, we now have a magnetic field, or an M field. And so, like, if I have this north-south magnet, I have a magnetic field around it. And if I start moving this magnet and I have like a copper wire around me, then current will start flowing through the wire. And we'll demonstrate this in class. Actually, what I will end up doing is I'll end up like hooking up a battery to a wire and sending charge through it, and then putting a magnet next to the wire, and you're going to notice that the wire is going to start moving. Why? Because in the same way, a moving electric field creates a perpendicular magnetic field. So I just want to introduce it to you here because I'm going to go over it more thoroughly in class. And this concludes our electricity and electrodynamics notes.